Bismillah ar-Rahman ar-Rahim. Welcome to lecture number 2 on probability, random variables and stochastic theorem. اليوم راح نتكلم عن بعض أو definitions of probability. راح نشوف 3 different definitions. راح نشوفهم برضو خلال دراستنا إحنا وياكم. راح نحتاجهم خلال الدراسة ونحتاج بعضهم لإثبات بعض النظريات وبعضهم حتى إذا بدنا نستخدم بعض الكمبيوتر simulations راح نحتاج بعض هذه definitions. Okay, so let's start. So today we'll talk about definitions of probability. The first definition, or let's do it this way, we will have 3 definitions of probability will be stated. Okay, the first one is the axiomatic definition. The axiomatic definition is a definition of probability based on axioms. The first axiom, or axiom 1, it says that the probability of an event A, namely probability of A, is a non-negative number assigned to this event. Mathematically, we say that probability of A is greater than or equals 0. It could be 0, but it should be always a non-negative number. So you have a non-negative number for any probability. Please be careful when you solve any problem and you get a negative probability, then you have to stop and say, I made a mistake. I have to go back and see what wrong did you do in solving this problem. Axiom 2, the probability of the certain event equals 1. And mathematics, probability of S, probability of the sample space or the certain event or the sample space is equal to 1. Okay. So the maximum that you can get, the minimum of probability is 0, the maximum is 1. You will never get a number larger than 1. This is by axioms. And axiom 3, if the events A and B are mutually exclusive or disjoint, then the probability of A union B is equal to the probability of A plus probability of B. And you can see this through the Venn diagram. If you have S, you have A, and you have B, and A intersection B is equal to phi. This is the disjoint condition. Then the probability of A union B is equal to the probability of A plus the probability of B. Okay, those are the three axioms that we have the definition of the axiomatic definition based on. Okay, let's move to the next definition. The second definition of probability is based on the relative frequency definition. Okay. Here it says that the probability of A of an event A is the limit probability of A is equal to the limit of n sub A over n, where n approaches infinity, when n is very large number. So if you do an experiment so many times, and you have NA occurrences of the event A, the ratio of NA divided by the total number of the experiment or the trials is equal to the probability of A, where NA is the number of occurrences of A, and N is the number of trials. Actually, this relative frequency definition is very good for doing computer simulations. Let's just make an example, a rough example. If you do an experiment for heads and tails, and you do this through computer, and you will say, or you can do it experimentally in class. You have a coin, and you have the heads and tails on the coin, and you throw the coin, let's say 10,000 times. So if you, let's say that if you throw or toss the coin, sorry, if you toss the coin 10,000 times in an experiment, and you found that about 5,000 times heads and about 5,000 times tails. This means that probability of heads is equal to 5,000 over 10,000, and this equals 0.5, and probability of tails is also equals 5,000 over 10,000. And this is equals also to 0.5. So 5,000 divided by 10,000, and this is NA over N as N approaches infinity, as infinity means a very large number. So you do the experiment very large, so many times to get an accurate result. Okay. The third definition is the classical definition. The classical definition. The probability of an event A is determined a priori without actual experimentation. It is given by the ratio P of A equals to NA over N, where N is the number of all possible outcomes and NA is the number of outcomes that are favorable to the event A. Okay? Okay, let's say, very simple, if you have S for heads and tails, you know, H and T, heads and tails, when you toss a coin. So you have two possible outcomes, probability of probability of H. So H is one of those events. It's only 1 out of 2, so it's 1 over 2. And probability of T is also equals 1 over 2. If we have another example, if we take another example, if we have S equals 1, 2, 3, 4, 5, 6. Those are all possible outcomes when you throw a die. So when you throw a die, you have 6 possible outcomes. يعني لما بترمي حجر النرد في عندك 6 أوجه. Okay. Probability of 1 is equal to 1 over 6, and probability of 6 is equal to 1 over 6. Okay. Let's see a different example here. In this example, we roll 2 dice. And we want to find the probability that the sum of numbers that show on top equals 7. So you roll 2 dice, okay, and we want to find the probability that the sum of numbers. Okay, so as a solution, we can think of this. Let me just use this classical definition. We need to find NA and N. Let me just think of it very simple, and we say, okay, we could consider as possible outcomes that we could consider as a possible outcomes, then we always have the same problem. Okay, outcomes, the 11 sums. What are those 11 sums? You know, you are throwing 2 dice. Each one of them, you could have 2, and we could have 3, 4, 5, 6, 7, 8, 9, 10, 11, and finally 12. So we have 11 sums. Both faces have twins, and we have 3, 4, 5, 6. Those are the 11 different sums that we can get from the possible outcomes that we have. So only one outcome is favorable, namely the sum equals 7. Hence, we can say that probability of sum equals 7 is equal to 1 out of 11 sums. Okay? So you have sum of 7 out of 11 outcomes, and the sum is 1 out of 11. But this is not true. This is wrong. Why it is wrong? Because this 2 has a probability different than this 3. This 2 is coming from 1 and 1, but this 3 coming from 1 and 2 and 2 and 1. So you have two outcomes that reach the sum of 11. If you have 4, you have 1 and 3, 3 and 1, 2 and 2. So you have more than one outcome that give us the sum of 4, and so on. So there is some misleading idea here. And to see the good or the correct answer, we have to see all the possible outcomes that have exactly the same probability, with equal probability. So for the answer for the true answer, I'm gonna make a table showing that if we have the first phase has 1, 2, 3, 4, 5, and 6, and the second phase of the die 1, 2, 3, 4, 5, and 6. So we have here 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, and 1 and 6. So these are possible outcomes, and every one of those has exactly the same probability. Now in the second one, you have 2 and 1, 2 and 2, 2 and 3, 2 and 4, 2 and 6. Third one, you have 3 and 1, 3 and 2, and 4, 3 and 5, and 3 and 6, 4 and 1, 4 and 2, 4 and 3, 4 and 4, 4 and 5, and 4 and 6, and here 5, 1, 5 and 2, 5 and 3, 5 and 4, 5 and 5, and 5 and 6, and lastly 6 and 1, 6 and 2, 6 and 3, 6 and 4, 6 and 5, and 6 and 6. So you have 6 times 6, you have 36. So your n is equal to 36. We have 36 different or possible outcomes. We are in favor of the sum when the sum equals 7. What values, what combination give me 7? It's all those, let me put them in with different color. So all those combinations are in favor of 7, equal 7. So 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. All of them have exactly the same probability, and all of them will give us a sum of 7. So this 7 is coming from 1, 2, 3, 4, 5, 6 different combinations. Okay? As for the 2 here, this one, for this sum, it comes only from one possible outcome, which is 1 and 1. This is the only solution that gives us this one. So the probability of the sum to be equals to 2 is 1 over 36. But the probability of the sum to be equal to the sum equals to 7. So the probability of the sum equals 7. It's equal to NA over N, and this is equals to 1, 2, 3, 4, 5, 6, 6 over 36, and this is equals to 1/6. Okay, so this is the correct answer. Okay. So what we can conclude here for the classical definition, is that we will have an improved version of it, and we will do it in this manner. So an improved version, an improved version of the classical definition. It states that the probability of an event equals the ratio of its favorable outcomes to the total number of outcomes provided that all outcomes are equally likely. And in this case, all the 36 outcomes have the probability of 1 over 36. So the probability of the simple events here, 1 over 36, 1 over 36, and so on. And this is how we solve this problem. So those are the 3 definitions that we have so far. I hope that you got the definitions very well, and we will use them in next lectures. Thank you.